Well, we're going to look in this lesson with centers of mass and moments of inertia, and also just the whole concept of moment. So suppose we have a planar lamina with a constant density rho. Then its mass is just going to be its area times that density, rho, whatever that may be. So for this region that I've pictured here, we've got the following equation for the mass. The mass is rho times the area, which is rho times the double integral over the region R dA, actually times 1 dA, 1 being you can think of it as height 1 above it. Actually, you could think of it as height rho above it if you wanted, since rho is a constant. So that's the double integral of rho times dA over the region R. And the way this particular one is drawn, you can see that our x is going from A to B, and our y, if we draw a stripe across the region, the upper part of the stripe hits a g2 of x, the bottom part of the stripe hits a g1 of x. We start making these stripes at x equals a and stop making these stripes at x equal b. So if I were to look at the way this is designed, you should see that the density times this double integral that will give us the area of the region is indeed the mass of the lamina.
Obi-Wan has taught you well.
I'm glad. So, suppose that the lamina is not of uniform density. Like the rho is not a constant. In other words, it might be more dense further from the origin or closer to the origin, or more dense further from the x-axis or closer to the x-axis, and you're probably thinking, well, laminas really aren't like that. If it's, a very thin slice of something, then it's going to be equally dense. And stop and think. But saying that our lamina has variable density would behave like an electrically charged plate. Some places there's more charge on the plate than others, so it does actually have some real-world application. So anyway, if we have a function rho of xy that represents the density at a particular point xy. So here's how we find the mass of a planar lamina of variable density. If rho xy is a continuous density function on the lamina corresponding to a plane region R, then the mass of the lamina is given by the double integral over the region R, and the region R will dictate what our limits of integration are, and then of rho of xy, that's our density function, times dA, and that's how you find the mass of a planar lamina of variable density. So instead of a rho here as a constant, it's rho of xy, whatever that may be.